Welcome to Chapter 6, Arrays. By the end of this chapter, you'll organize data using arrays, explain how arrays simplify and replace nested decision structures, implement constants to work with arrays, locate exact matches within an array, use parallel arrays effectively, search an array for values within a range, ensure operations stay within an array's bounds, and use a for loop to iterate through and process array elements. An array is a data structure that stores multiple values of the same type in contiguous memory locations. That gives you efficient storage and retrieval, an organized way to represent data, and a much simpler way to handle groups of related values. Instead of separate variables for a list of employee names, you'd store them all in one array, declared with curly braces in Java and C++, or square brackets as a list in Python. Declaring an array reserves a contiguous block of memory for its elements. Each element is accessed by an index or subscript, and indexing always starts at 0. The array's total size gets specified at declaration, or adjusted dynamically depending on the language. Declaring an array called prices with size 3 reserves exactly 3 memory locations: prices 0, prices 1, and prices 2. Because array elements are stored contiguously, they sit one after another in memory. If prices starts at address 1000 and each element takes 4 bytes, prices 0 is at 1000, prices 1 at 1004, prices 2 at 1008, and so on. The element size itself depends on the data type. And since indexing always starts at 0, an array declared with size 3 is only valid for indices 0, 1, and 2, never 3. Every element in an array shares the same data type, and that contiguous memory layout is exactly what makes access so fast. Indices always range from 0 to size -1, with each element uniquely identified by its own index. And array elements can be used directly in arithmetic or logical operations, just like any other variable. Here in Java, numbers 0 plus numbers 1 gives you their sum, just as naturally as adding 2 separate variables would. Here's array creation, assignment, and math as actual C++ code. Declare an array of size 4, assign a value to each index, perform arithmetic directly on the array elements, sum, difference, product, quotient, then loop through and print everything. Notice the output confirms each calculation matches exactly what you'd expect from the assigned values. Here's that same array creation, assignment, and math example in Java. Same 4 values assigned by index, same 4 arithmetic operations performed directly on array elements, and a loop using numbers.length to print each one, producing identical output to the C++ version, just with Java's own array length syntax. And here's the same example in Python, using a list instead of a fixed size array. Numbers equals 0 times 4 creates 4 0 initialized slots. Values get assigned by index just like the other languages, and the same 4 calculations run. Note Python's double slash operator for integer division, since a single slash would return a decimal instead of matching the other 2 languages' output. Looping through an array lets you access or manipulate every element efficiently, displaying values, modifying them, or summing them up. A traditional for loop with an index gives you full control, while an enhanced loop, like Java's for each or Python's direct iteration, is simpler when you don't actually need the index itself. Either way, make sure your loop's range dynamically matches the array's actual size, using length in Java, len in Python, or a computed size in C++, never a hard-coded number. Here's looping through an array as actual code, in C++, Java, and Python. Each version calculates or retrieves the array's size, then loops through printing every element alongside its index. Notice C++ has to manually compute size by dividing total bytes by one element size, while Java and Python both provide that size directly through length and len. Arrays can replace long chains of if-else statements or switch cases entirely. They simplify logic by avoiding repetitive conditional structures, reducing the risk of errors that come with complex nested logic. They enable scalable code, handling a variable number of cases without ever touching your control structures. Adding a new category is as simple as resizing the array. And they improve efficiency, since direct indexing gives you faster lookups and updates, especially paired with a for loop. Here's the difference in Java. Nested if-else-if statements counting occurrences of 0, 1, and 2 requires a separate counter variable and a conditional branch for every possible value. The array version instead uses a single counts array, incrementing counts, number directly. No branching at all, and it scales effortlessly if you ever need to count more values. Here's that same nested if versus array comparison in C++. The nested version needs one counter variable and one conditional branch per value being counted, while the array version replaces all of that with a single line, counts number plus plus, inside the loop. Same result, dramatically less code. And here's the same comparison one more time in Python. Nested if-elif branches versus a single counts list incremented directly by index. Across all 3 languages, the pattern holds. An array turns what would be several conditional branches into one simple, scalable line of code. Arrays commonly use 3 types of constants. For array size, a named constant like size, avoids hard-coding a raw number everywhere it's needed. For element values, constants represent fixed values that won't change, like the months of the year. And for indexes, named constants replace plain numbers with meaningful labels. Indiana equals 5, for example, is far clearer than just seeing the number 5 scattered through your code. The payoff: more readable, more maintainable code, with less risk of hard-coding errors. Here's named constants in action. In C++, days_in_week, Monday through Sunday, are all declared as constants, then used directly as array indices. Temperatures, Monday, equals 70, for example. Compare that to writing temperatures, 0, directly. The named constant version is instantly readable, telling you exactly which day you're working with. Here's that same named constants pattern in Java. Days_in_week, and each day of the week declared as static final constants, then used as clean, self-documenting array indices throughout the rest of the program. Temperatures Monday, temperatures Tuesday, and so on, exactly matching the C++ version's logic. And here's the same pattern in Python. Each day of the week defined as a constant, then used to index directly into the temperatures list. Temperatures Monday, temperatures Tuesday, and the rest, reading just as clearly as the Java and C++ versions, even without Python enforcing true constants at the language level. Linear search is the simplest way to find an exact match in an array. Just iterate through every element until you find it. It works on unsorted arrays, though it gets less efficient as the array grows larger. A search can return either the matching index itself, or simply a true or false result confirming whether the value exists at all. Linear search is easy to implement and perfectly fine for small arrays. For larger, sorted datasets, a more efficient algorithm like binary search is usually the better choice. Here's linear search as actual C++ code. The loop checks each element against a target value, and if it finds a match, it prints the index and stops immediately with break. Searching for 30 finds it at index 2. Change the target to 60, which isn't in the array, and the found flag stays false, printing a not found message instead. Here's that same linear search logic in both Java and Python. Loop through the array, compare each element to the target, and break out the moment a match is found. Both produce identical output to the C++ version, 30 found at index 2, or a not found message if you search for something that isn't there, like 60. Parallel arrays are separate arrays where elements at the same index across each array represent related data, letting you store and process connected information without building a more complex structure. They're ideal when each array holds one specific attribute of related items, like names, prices, and quantities together. The trade-off: parallel arrays lack the encapsulation that objects or structs provide, so they get harder to manage as relationships grow more complex, and keeping every array's indexing in sync takes real care. Here's parallel arrays as actual code in C++, Java, and Python. Burger names and burger prices are two separate arrays, but index 0 in one always corresponds to index 0 in the other. Looping through both together, using the same index, builds a complete menu, name and price paired correctly for every item, across all three languages. Always validate that an index falls within an array's valid range, 0 up through length -1. Accessing an invalid index can throw a runtime exception, like Java's array index out of bounds exception, or cause outright undefined behavior in C++. The safest approach: use loops that iterate up to the array's actual length rather than a hard-coded number, so your code stays correct even if the array's size changes. Most languages also provide built-in helpers, like length in Java or len in Python, to make this easy to get right. Here's the difference between correct and incorrect bounds checking in C++. The correct version uses I less than size, keeping every access safely inside the array. The incorrect version uses I less than or equal to size instead. That one extra iteration reaches past the array's last valid index, triggering undefined behavior the moment I equals size. Here's that same correct versus incorrect comparison in Java. I less than numbers.length stays safely within bounds, while I less than or equal to numbers.length reaches one index too far. And unlike C++'s undefined behavior, Java throws an explicit array index out of bounds exception the instant it happens, making the mistake much easier to catch. And here's the same comparison in Python. Range, len numbers, stays correctly within bounds, while range, len numbers +1, pushes one index too far, raising an index error the moment the loop reaches that invalid position. The exact same underlying mistake we just saw in C++ and Java, just producing Python's own specific error. No new assignment this time. Just make sure your Canvas assignments are complete, and bring yourself to class ready to learn. We'll be building directly on everything covered in this chapter, so come prepared to work with arrays hands-on.